My name is Mahad, and I'm going to be taking you through machine learning with Visha Balam. To begin with, our first slide, what is machine learning? Machine learning, basically, we are talking about teaching computers to learn from clean data to increase their performance instead of being explicitly programmed. Basically, it's a subset of artificial intelligence that focuses on teaching computers to learn from data and improve their performance over time without being explicitly programmed. Uh, Here, instead of us writing step-by-step instructions for a task, machine learning allows the computer to analyze the patterns in the data and make decisions based on those patterns. For example, okay, imagine if you have your computer, if you want your computer to identify whether an image is of a cat or a dog. So instead of writing a detailed code for every possible scenario, uh, it might be you can train your computer with thousands of images of cats and dogs. So the computer learns to recognize patterns in these images. Uh, for example, okay, cats often have whiskers, while dogs often have floppy ears. So the algorithm uses these patterns to make predictions. Uh, we also have types of machine learning, and they are basically two. We have supervised and unsupervised. So under supervised, uh, here, as I said, it involves teaching a computer with a human labeled data sets, which provides necessary supervision during training time. Uh, Basically, here the computer is trained using labeled dataset, where each data point is paired with its correct output. The goal here is to learn a function that maps inputs to correct outputs. And here we basically have like two steps. We have the input-output pairs, where the algorithm observes examples of inputs and their corresponding outputs, which are the labels. And also have the learning function. Here, the algorithm tries to generalize the relationship between the inputs, outputs to predict outputs of unseen data. The example I can give you is if you are trying to to determine prices of houses. Here, the dataset that you have the input which are the features. Let me say the square footage, number of bedrooms, and the location. Then the output that you need is house price. So you provide the algorithm with historical data such as the square footage. Let me say that can be like, it can range, let me say 1,500, 2,000. The number of bedrooms, they can, let me say like 3, 4, 5. Even the location, it can be urban or suburban. Then you attach the price label. So the algorithm will use this historical data to determine any price of a house depending on like the data that you have provided. Mainly, the goal here, the algorithm learns the relationship between the features and the price. For okay, applications that can be used here, it can be applied in email spamming filters, where the model learns to classify emails as spam or non-spam. It can also be used in self-driving cars. Here, the model learns from labeled data, like let me say images, pedestrians, traffic lights. Then I'm moving on to unsupervised machine learning. Here, okay, the computer works with unlabeled data and tries to find hidden patterns or structures in the data. Basically, here we have we don't have labels, whereby so the algorithm doesn't know the correct output. It only has the input data. So the algorithm groups data into clusters with similar data points. For example, okay, it will get the data that has similar characteristics, all features, to group it like together. This will help to reduce data sets complexity. The example I can give you, if you are, let me say, if you have customers and you want to group them, and the only data that you have about these customers is like, let me say, You have like age, income, and purchase behavior, but there are no labels attached to them. Like, let me say, these ones are high spenders, these are budget shoppers. So, that, what's the task here? You have to group the customers into clusters based on their similarities. Let me say the cluster one will have a, let me say, according to age, you have young customers with low income, but they make frequent purchases. Then the next cluster will have, let me say, like old customers with a high income, but they make occasional big purchases. Uh, then moving on to the next one, we have concepts that you need to know in machine learning. To begin with is the data set. So what is a data set? Uh, you can say this one, it's like a backbone of any machine learning project, and that actually contains the data your model will use to learn the patterns and make predictions. It consists of typically two features. Like it has the features target, where the features are the input variables, like age. Then the target is the output variable. Then we have selecting and training a model. This involves choosing the right machine learning algorithm based on the problem type and training it on the data. Then we also have performing EDA, which is explanatory data analysis. This one involves analyzing and visualizing your data to understand its structure, detect the patterns, and spot issues. Then things that we need to know, three things for a machine learning model. So the first one, we have the prediction model. Here, the prediction model maps input features to output. It's the core mechanism for any machine learning algorithm. Then we have the cost function that this one compares the predicted value with the actual value. Then we have the optimizer. This one basically adjusts the model parameters. Then moving on to the next slide, we have a machine learning pipeline. First of all, what's a machine learning pipeline? This one is a step-by-step process to develop or deploy and maintain a machine learning model. Under this, we have like steps. First one, we have you get the data, you perform the EDA, then you prepare the data for machine learning algorithm, you select a model and train it, you fine tune the model, you present the solution, then you launch, monitor, and maintain your system. My colleague will continue from there.
So that was it from my colleague, Mahad. Thank you. My name is Bala Mugesha, and I'll be starting, of course, from where he stopped. And I stopped on, of course, the end-to-end machine learning pipeline. I'll be starting from KNN. So what do you understand by KNN? KNN is basically K nearest neighbors, and they're telling us that it is an instance-based learning used for both classification and regression tasks. So the K in KNN, of course, represents the number of nearest neighbors to consider. So for instance, if my K is equal to 3, then my algorithm, of course, will look at 3 neighbors to classify or make a decision. So let's say I'm in a new neighborhood and I want to, of course, decide whether I'm supposed to play maybe basketball or football. So if my K is equal to 3, that means that, for instance, the 2 neighbors play football and maybe the one neighbor plays volleyball or basketball. So for me to make a decision, I'll base on what we call a majority vote, or the number of people that, of course, have a higher say. And in that case, there will be, of course, players of football. So I will choose to play football just because I have 2 people that, of course, I can join, not the one person that is lonely or an introvert. So the steps are calculate the distance between all the training data and the test point, find the nearest neighbors by sorting the pairwise distances, and of course classify the point based on the majority vote like I explained. So that's it from KNN. And our next slide talks about decision trees. So what are decision trees? Basically, they're telling us that decision trees are data structures that are composed of nodes, branches, and leaves. So basically, we use algorithms like ID3, that is iterative dichotomizer, to draw these trees. So what strategy or what criteria do we use when we are drawing these trees? So we calculate the entropy of each variable by, of course, getting its values and calculating the entropy to see how much information is each value under a certain variable is giving us. So we are going to draw the tree whereby on our root node we have a variable that is giving us maximum information in order to make a classification. So in this example, we have four variables, that is outlook, temperature, humidity, and windy. And the classification we have here is either the Platonist, that is the no and yes. That's the target variable that we are looking at in this kind of scenario. So the new instance that is coming in, we are supposed to classify it basing on a variable that is giving us maximum information. And like I told you, we're going to calculate the entropy. Entropy is basically a means of calculating or calculating uncertainty or impurities in data. So we're going to calculate the entropy of each value under a certain variable. Then you get the information gained by getting the entropy of the whole data set, then subtracting the individual entropy from the independent variables. So that's how we can get the information gain. And when I tried calculating the information gain, Outlook had the maximum information gain. Yeah, it was around 0.29 for something. So that's why I have it here on my root node in this decision tree. And later on, I, of course, proceeded to the values that I had in my new instance, that was sunny, overcast, and rainy. So at the end of the day, I classified overcast uh, as yes, in that it had four straight yeses for all the days, day 3, day 7, day 12, and day 13. It had constant yeses, so it didn't have a no. Then sunny and rainy had mixed yeses and no's. So I classified the new instance to be yes, the Platonist, because of those rules. So that's how ID3 algorithm works. So to proceed to linear regression, linear regression is mostly used in statistics. Yeah, it's mostly used in statistics. And it works by finding, of course, the line of best fit through a set of data points. So I can plot these data points, say the predicted data points and the actual data points. And of course, I'm going to draw the line of best fit or the regression line uh, to see how far or how close or how much errors I have in between, of course, the actual data and the predicted data to see how good, of course, the model is actually performing. So let's say we have an example of maybe an independent variable X uh, with features or inputs like hours worked or years of experience, and a dependent variable Y. Yeah, mark this, a dependent variable Y. And this is the outcome that you're going to get at the end of the day. So I think like my colleague talked idea, we have inputs and of course we have outputs. So like you explained under supervised machine learning, we have labels that guide you or guide the function that is going to give you the output by the input and output pairs that you first feed to the computer. So in this case, the dependent variable is going to help us basically for the output. And the output in this case, we are predicting something like salary, price, and yeah, price of the house. So the equation of the line is of course y is equal to mx plus b. So linear regression assumes that the relationship between variables can be described by that equation of the line or the line of best fit or the regression line like I explained earlier. So the y dependent variable is going to help us the x independent variable is going to help us predict the y dependent variable, in that we can tell how uh what house you can buy according to the salary you're actually getting at work. Yeah, so we are using the independent variable to predict the dependent variable. So that's how linear regression works. So we have something called logistic regression. This is related to what you call sigmoid. Sigmoid is an activation function that helps us to introduce non-linearity in models. Yeah. So remember, real world data is not as direct. So we always have to like introduce non-linearity to help us predict models or predict unseen data. Yeah, data we haven't seen. And the function we use is a sigmoid function, in that it has 1 over 1 plus the exponential of the negative x. And yeah, the applications like my colleague talked earlier, we have spam detection, yeah, medical diagnosis. And this could be the pictorial representation. We have maybe work experience and predictive getting promoted. So if you have the more the work experience, the more the chance of being promoted. And this is always how do I explain? It's like probability, because it ranges from 0 to 1. So if you have like more than 0.5 probability, then you're going to have a chance of being promoted. If you have less than 0.5 probability, then you have chances of not being promoted. So it basically helps us in binary classification, whereas have like two ways to beat around it. Imagine you're like predicting maybe fruits, and it being binary, you're either predicting maybe an apple or an orange. So you can set your model to learn such in a way that if you have above 0.5 probability, then you're going to classify the fruit to be maybe a mango. If you have less than 0.5 probability, then you're going to classify the other fruit as an apple maybe. So that's how it works. That's how logistic regression works. It uses sigmoid functions, and can basically be based in binary classification. So we have ensemble learning. Ensemble learning basically combines multiple models to achieve better performance and accuracy. And yeah, in the to increase accuracy and the robustness in individual models. So it uses these two types. We have banging and of course boosting. So the way banging works, it creates multiple independent models by using random subsets of data and aggregate results, such as average for regression, majority vote for classification. So it can work under the two tasks, regression and classification. And boosting works in a way that it builds models sequentially, whereby each new model focuses on correcting the errors on the previous one. So under each model, we're trying to like reduce a certain error. So we reduce a certain error under a certain model. Then when you go to the next model, still we are reducing another error, but using of course the new model. And if I'm running out of time, so if I'm to proceed to random forest is also an ensemble method used on the banging technique and decision trees. I explained decision trees earlier. So we can build on multiple decision trees during training, and we also combine their outputs for their accuracy and generalization. And it combines, of course, multiple decision trees using banging. I think you know what decision trees are at this point. So let me go to my last concept, which is support vector machines, SVM. Support vector machines helps us to classify or split classes into two. So we have both linear support vector machine and of course non-linear support vector machine. So the way it works is you're given positive and negative examples. So you're going to, of course, add a bias, or the first step is always, of course, to plot the data, get uh, the data points that are close to the line that separates the two classes. Then you're going to get those data points that are close to the line that separates two classes, you add a bias to them. Okay, you add a bias to them, then you're going to calculate the alpha, of course, using this method, vectors. Yeah, as you can see, S1 alpha 1, S1 alpha 2. Then you can later on, because of time, I'm going to skip this, but you can later on like separate the two classes or the two data points according to a line that of course splits the two classes. Then for non-linear SVM, which I did include in the slide, you're just going to move data points to the next feature space. Yeah, to of course introduce a way you can separate the data points into classes for easy recognition of patterns. Then the last concept here is principal component analysis, whereby its purpose is to basically reduce dimensionality while retaining variance. So for you to understand patterns, it's easier to like reduce that dimension. I'm trying to explain this in such a way that if 2D, you all know that 2D is easily understood by humans compared to 3D. So we're trying to like reduce our data from 3D to 2D by, of course, eliminating unnecessary concepts or unnecessary information that is not going to help us in predicting the patterns. Then model evaluation metrics. I think let me just stop on overfitting and underfitting. Overfitting is when the model is too complex and performs poorly on unseen data. It could work well on the training data, but when you bring in the testing, I mean the evaluation data, then it works very poorly. It predicts things that are actually not covered. Then underfitting is when the model is too simple and fails to capture patterns in data. So you can notice a difference in the and the solutions to this can be regularization or bringing in more data or pruning. I think that's it from me and my colleague Semwanga Mahad. I remain Balam Gisha. Have yourselves a good day. Thank you.
Use 15 minutes.
Yeah, man, I noticed it. Fuck. I noticed it, but I couldn't do anything. I ever explained some things. Uh,
And you go up.
is that-